Alright, this is the business calculus video for section 4.2, part 1, and we're talking about logarithmic functions. So we're going to introduce logarithmic functions and emphasize the natural logarithmic function, and we're going to apply those logarithms to a wide variety of problems, from doubling money under compound interest to drug dosage. So the word logarithm, which is abbreviated log, means power or exponent. And the number being raised to the power is called the base and is written as a subscript. So for example, the expression log base 10 of 1,000 means the exponent to which we raise 10 to get 1,000. So 10 to the third equals 1,000, so the exponent is 3, meaning the logarithm is 3. Okay, so the way we would say this is log base 10 of 1,000 equals 3. So we're going to find any logarithm by writing them as exponents and then finding what that exponent is. So we'll be able to switch these over. Since log base 10 of 1,000 equals 3, we know that 10 to the third power equals 1,000. Okay, and we're going to be able to switch back and forth between the logarithmic and the exponential in order to solve problems. All right, let's keep going. So this first example, we need to find each logarithm. So in the first one, I have log base 10 of 100, or in other words, 10 to the what power equals 100? We know that that is 2. On the next one, I have log base 10 of 1 over 10. So 10 to what power equals 1 over 10? And we know that 1 over 10 is the same thing as 10 to the negative 1. So 10 to the x equals 10 to the negative 1. So that gives us that x has to be negative 1. Okay. And the last one, I have log base 9 of 3. So that's 9 to the what power equals 3? Well, I know that the square root of 9 gives me 3. So that would be square root is the fractional exponent 1/2. So 9 to the 1/2 power equals 3. Okay, so we've shown this a little bit, how to go back and forth between the logarithm and the exponential. And on this next slide, we see, all right, so logarithms to the base 10 are called common logarithms and are often written without the base. So that log of 100 actually means log base 10 of 100. And we may find logarithms to other bases as well. Any positive number other than 1 can be used for a base. So in general, if we have log base a of x equal to y is the same as a to the y equals x. This is one of those you'd want to put on your note cards. Okay, so log base a of x equal to y is the same thing as a to the y equals x. And it kind of forms a little circle. A to the y equals x. Or log base a of x equals y. So you've got a little circle type thing that's happening there. All right, let's keep going. So the most widely used of all bases is base e, which we learned in section 4.1. So remember, that's the number approximately 2.718. And logarithms to the base e are called natural logarithms, or Naperian logarithms. So the natural logarithm of x is written ln x, n for natural, instead of log base e. Okay, so in other words, x is the power to which we raise e, to get in x is the power to which we raise e to get x. Okay? So what does that look like? If you remember this here, that our e to the x function looks something like this, where it's crossing there at 1. Pretend it's a pretty curve, right? Well, ln of x, that y equals ln of x, is the inverse function. So what we do is we flip it over, and you've got the graph that comes up along the y-axis and then continues up slowly. Where an exponential function was a very fast climb that grew very quickly, our logarithmic function is a slow climb. Right? They're not going to grow as quickly. The domain and range do flip. In this case, our domain is from 0 to infinity, and our range is all real numbers. Okay, so that flips from what it was with our exponential functions. All right. So, again, notice that the graph of ln x is always increasing and has y equals, or the y-axis as the vertical asymptote, and the natural logarithmic function can be used for modeling growth that continually slows. Yes, the growth is happening, but it's not happening very fast. All right? And if your logarithm has a different base, you can see on slide 8 that you see the graph for multiple different bases for logarithmic functions. If that base is greater than 1, so this is where your base is greater than 1, we have an increasing function. If your base is between 0 and 1, we have a decreasing function. All right. So what are some rules that we can use? Well, some rules that'll come in handy for logarithms are some properties that will come in handy. By learning these properties, by memorizing these properties, it will actually make the calculus part of this go a lot faster. So it's something that we want to practice. All right, so since logs are exponents, each property of exponents can be restated as a property of logarithms. And the first three properties show that some natural logarithms can be found without using a calculator. All right, so if you have ln of 1, that's equal to 0, and that's since e to the 0 power is 1. Okay, and that works for any logarithm. Log base 100 of 1 is equal to 0. And these properties go for any base. Okay. The next one is ln of e is equal to 1. All right, so if your base and your big number are the same, they're equal to 1. If you have ln of e raised to the x, it's equal to x. E to the ln x is also equal to x. These are some good ones to put on your properties or your flashcards. So on the first one, on example 4, I have ln of e to the 7th power. So that would be just 7. Because what's happening behind the scenes here, is ln, let's try that again. Ln, good grief, sorry. Base e of e to the 7th power. This ln of e to the e is gone, which just gives us 7. So the same thing would happen on b, that ln e kind of cancels itself out, giving us 3x. On part C, same concept, but we want to take the cubed root of e squared and rewrite that. So you have the ln, I keep adding extra letters here. Ln of e to the 2/3 power. So that would just be 2/3. And then on the last one, this DE to the ln 5 follows property 4 on the slide ahead of this. So E to the ln of 5 is just equal to 5. All right, so those are some basic properties that work for natural logarithms. Here's some more properties that work for all different types of logarithms. Come on. And again, these are ones that you'd want to put on a note card. So these properties work for any logs. Doesn't have to be natural logarithm. It's going to work for anything. But if you have the natural log of m times n, that's equal to ln of m plus ln of n. So the multiplication becomes an addition if we break it apart, if we expand it, okay? And we could also go from the addition and simplify it down as well. On the next one, ln of 1 over n becomes negative ln. Then we have ln of m divided by n becomes ln of m minus ln of n. And the last one we refer to as like a power rule. The ln of m to the p power, that p comes out front. So p times the ln of m. All right, so how do we use these? We're going to use these to simplify expressions or to expand them out. Again, this is going to help us when we go into the calculus part of it. We're going to be able to simplify these problems very quickly, either expand them or condense them, and make the derivatives a lot faster. So here on the first one, ln of 2 times 3 would become ln of 2 plus ln of 3. Okay, the multiplication breaks up as two separate logarithms and addition. On B, you've got property 6 that helps you here. This just becomes negative ln of 7. If you don't remember that one, it's not a huge deal. What you could also do is, we know division breaks up as subtraction. So I have the ln of 1 minus the ln of 7. And if you recall, the logarithm, any logarithm of 1 is equal to 0. So that's 0 minus ln of 7. And that's where that negative ln of 7 is coming from. Then on C, again, the division breaks up to subtraction. So I have ln of 2 minus ln of 3. And on D, the power rule brings that 3 out front. I have 3 times the ln of 2. And then you're done. All right, we can still work some more on example 6 on slide 13. And in this one, they're already broken apart, so we're actually going to condense it in, okay, and simplify these a little bit. So on part A, I have ln of 2x minus ln of 2. Well, they can combine this as ln of 2x divided by 2, which would just simplify to the ln of x. That's a much simpler problem to mess with. On the next one, that division here in the very first part, ln of x divided by 3, can break apart. So I have the ln of x minus the ln of e plus 1. And if you recall, go back and look at our slide 9. ln of e is just equal to 1. So this is equal to 1. So I have negative 1 plus 1, which simplifies to just ln x. On this next one, actually I want you to try to simplify C, and I'll come in on the next video and show you the answer.